let us look at another example today, which is quite different from what we have seen. Okay, so this is a 7-link mechanism. So anytime you encounter a new mechanism, it's probably a good idea to do a mobility check. Okay, can you do a quick mobility check on this? So this is actually a mechanism with mobility equal to 2. Okay, the fact that the number of links were not even, because that is a condition for mobility to be equal to 1. Okay, that itself should have given you a clue that this is likely to not have a mobility of 1. And there are no ideal degrees of freedom either. So it is a true blue mobility equal to 2 mechanism. Okay. So that means it needs 2 inputs, 2 velocity inputs. So let us say link 2 rotates at some omega, say 1.258 clockwise, and the hydraulic actuator, so say this is O2, A, B, C, D, and this is O7. So the hydraulic actuator DO7 expands at a rate of 10 centimeter per second. So you want to find omega 5 at this instant. Okay. So what you are given here when you say the hydraulic cylinder DO7 expands at that rate, I am given the relative velocity between 6 and 7 along that. Okay, so that's the relative velocity component that I know. So I don't know the absolute velocity of D. Would D have some other component of velocity as well? Because of rotation about O7, it would have a component which is perpendicular to O7D, but I do not know what that is because I do not know omega 6 or omega 7, both of which will be equal obviously here. So this is not a typical problem that you could solve using your velocity difference method. Instant centers also you can try, but you will find that this is not really amenable to that. So, what we will look at applying the auxiliary point method to this, to solve this problem. So, let us take the ternary link, right, CBD. This is the floating link. Okay. I know the velocity of point A, okay, point A. So, B, C, D are my motion transfer points to this ternary link, and this is actually, it is called, this is a mechanism that is considered a mechanism with a high degree of complexity, kinematic complexity, because so the kinematic complexity comes from, so a mechanism is kinematically complex if it has a ternary or higher order floating link. And if I do not know the path of two of the motion transfer points on the path curvature of two of the points, motion transfer points on the ternary link, then it is called a mechanism with a high degree of complexity, right. Here I know the path curvature for point C, because link 5 is pivoted to the ground, but B as well as D in this case I do not know, and even if I try inversion or something like that, I am not really going to, it is not easy to determine this one, okay. It is not simple mechanism. So, this is, so let me just write down the definition of if the radii of path curvature of at least two motion transfer points links are known, the mechanism has a low degree of complexity, otherwise it has a high degree of complexity. So, DOC is degree of complexity. Okay. So, in this case you have a mechanism with a high degree of complexity. So, let us try the velocity analysis using the auxiliary points. So, let us look at the ternary link of this. Okay, I have this link. I will just for clarity just explode, and with it has the motion transfer points B, C and D. Okay. And I know the velocity of point A. So, I am given omega 2 here and I am given this velocity here. Okay. Those are the two things I know, two velocity inputs I have. I have omega 2 and I am given the velocity at which this hydraulic cylinder is expanding. Okay. So, if I look at A, I know the velocity of A completely, right. So, this would be the velocity of A. So, this is known completely and B is a motion transfer point. So, I can take an auxiliary line from A through B, take that as my first auxiliary line. Okay. Now, there is another velocity I know, which is this velocity here, and that is along this line O7D. Okay. So, the other component of the velocity is perpendicular to this. So, that is not going to be transmitted. So, if I take an auxiliary line which is, say if this is my O7, you know, which is along this, okay, then I know the component of the velocity that is transmitted, because I know that velocity, this v. Okay. So, I have v that is being transmitted in this direction. The other component is perpendicular to O7D and therefore, is not transmitted through this, along this line. Through some other line, yeah, but along this line it is not transmitted. So, now if I look at this auxiliary point x, I know two components along two different directions. Okay. So, I know, so if I take this is VA along 1, that is going to be transmitted through B to x. So, this would be Vx along 1. Okay. The second one is this V transmitted through D, and that will be equal to this. So, these are two components that I know. Okay. So, that means if I draw the perpendiculars to these two, the velocity vector for that will lie on the intersection of those two. So, if this is my point of intersection, rename this. Okay. Then this gives me, what is this? This gives me the velocity of x. Okay. So, now I know the velocity of one point on the, I still need one more. So, I need one more auxiliary line, right. So, one thing that I know is O5C. Okay. This is necessarily the O5x, okay, and O5, I don't, so x I know the velocity, but this is not purely rotating about O5. Okay. So, I cannot consider O5 and x to be on the, Okay, so you're in case of AB, so your question is, can I draw O5, the third motion, the third auxiliary line from O5 to X?
We cannot draw because it's not a motion transfer point.
Yes, X is not a motion transfer point.
But can we use it?
How would you like to use it? If you want to use it, how would you like to use it? Okay. So, this method relies on how the motion is transferred through the motion transfer points. Okay. So, with this, if I look at, there is one more motion transfer point through which I can draw the third auxiliary line, and I do know something about how the motion is transferred through this point C, right, because CO5 is, so I can draw, let us say I draw the third auxiliary line through C and X, because now I know the velocity of X is also on this coupler, and I know the velocity of this. I know another component also for the velocity of C. See, that is the thing. I need to have, to determine the velocity of any point, I need two components. I need two components. So, now because I have the velocity of X completely determined, I can draw the third auxiliary line through C and X. Now, I can find the velocity of X along the line 3, and that is what is going to be transmitted, that is going to be the same as what is transmitted through C along that line. So, if this, so this one here will be equal to Vc along 3 will be equal to Vx along 3. So, the other thing I know is, because how is it? How is this an auxiliary line? No, no. So, it is a point for which you know the velocity. Okay, you want to find two directions for the velocity of a point, right. Now, I know the velocity of point x. Okay. So, I know the, if I draw the auxiliary line connecting C, see D, X, C, they are all now points on the same body. Okay. So, that is the basis for what we are doing here. They are all points on the same rigid body. So, if you take any line, there the velocity that is transmitted has to be equal, because the distance between those do not change. So, if I know the velocity of x and I draw the auxiliary line Cx, then this velocity Vx along 3 will be equal to Vc along 3. I am kind of working backwards now.
In case this kind of does not strike us, drawing a line through CO5 and then getting a second point is also alright.
Drawing a line through CO5, okay.
And then it will either intersect with lines 1 or 2 somewhere else.
If it does, yes, yeah, you can do that, because you can, in this case, so for instance, so if I have C, maybe actually in this case probably say O5 is here, right, you can do that, you find another point like that. Instead of I can find another, let me see if I can so I know that the velocity, the absolute velocity of C has to be perpendicular to O5C.
If we draw a line through O5C, we
Mm.
do not know the velocity of the link because the angular velocity of O5 is.
We do not need, see we are talking about, so say this is O5, right. So, you are saying let me take CO5, an auxiliary line through CO5. What I know about C is that 0 velocity is transmitted. So, the necessarily I know that the velocity of C is perpendicular. This is exactly what I am going to use, but I need another point also. I need another velocity component for C. Okay, that is what I used x for. Okay. So, I have this is one component, let us say I already have this now, right, from x I have this. The other thing is, if I know that the absolute velocity has to be perpendicular to O5C, right. So, that means this would actually be like a very short. So, if this is the other component is perpendicular to this, so the other velocity is this, right, and the sum of these two components should be perpendicular to O5C. So, that is, so these two will not meet that is the problem here. Essentially these two perpendiculars have to meet, okay, because of my choice of the. So, let me just write down the steps instead. Okay. So, you have Vc, one component is Vx3.
Can you just assume that x intersects somewhere else?
X intersects somewhere else, yeah. So, if you assume x intersects somewhere else, okay. So, let us say x was here and we get let us say Vc along 3 is along this direction, then I have the head of the velocity vector Vc should be on that line, and it should also be perpendicular to, so if this is O5 here, okay, it should also be perpendicular to O5C. So, wherever these two meet, right, that point will give me the absolute velocity of C. Okay. So, this, because it resolves into these two perpendicular components. Okay. The problem was with the choice of my x. So, if x is somewhere here, then my problem is solved. Okay. So, this would be my third auxiliary line. I could have picked, so I can pick out of 1, 2 and 3, I can pick some other auxiliary point also, you know, whatever is available in the in my working area. Okay. So, this is the, so once I do this, now I have the absolute velocity of C, which means I can find omega 5 will be this by O5C, and the direction would be, in this case it would be clockwise. Because of the direction of this velocity. How is the second auxiliary point chosen? So, in this case I am just, so an auxiliary point comes at the intersection of two auxiliary lines. Okay. Here there could actually be another auxiliary, in this case it is no. So, here I have taken the third auxiliary line between C and X here. Okay. So, I am using one auxiliary point, and instead of and I am using C directly.
So, C is the auxiliary point.
C is the auxiliary point in this case.
And the second line,
No, but there is the second, no, here it is not because I know something about the absolute velocity of C. Okay. Otherwise, I could take another auxiliary line. So, here I have, let us see what are my other possibilities for auxiliary lines. I can take, suppose I take the auxiliary line through C and O5. Okay. Then that would intersect 2 and 3 at some other points. I can take any of those points, I can Y and Z. I could take those as well. Here, because directly I can find velocity of C, I use C. I could just take the third auxiliary line instead of between C and X. So, instead of taking the third auxiliary line, through C, okay, I could take the third auxiliary line along C and O5. Okay, say this is in the direction, this is along C and O5. Then I have Y, I have Z also. I can choose any one of those. Again the same thing, velocity of X I know along that auxiliary line, I apply that to Y, then do that. Okay.
so we are finding AC without calculating omega 3.
Yes, yes, yes. So, if I want omega 4, I would need Y or Z. Okay. So, Y or Z will give me omega 4. Finding velocities of Y or Z will give omega 4, and then I can use that to find that. Here, without finding omega 4, I can directly find omega 5 by taking C as my auxiliary point.
Even omega 4 can be found, right? You have 2 points on the body.
Yeah, once you find that, you can find, because I already know the velocity of 2 points. If I know the velocity of C and I know the velocity of X, that is all I need to find omega 4. So, I can do that in one shot basically if I take C. Here I would find this, and then I would have to find omega 5, because from this, from omega 4 I will find the velocity of C and then calculate omega 5. Okay. So, this is the auxiliary point method. So, for example, we have not really analyzed these kinds of mechanisms before, complex mechanisms by any of the regular methods. So, the perpendicular component at D is not transmitted, so we are not really concerned. So, in a practical situation, this is probably what you are going to know. If you know the hydraulic actuator, you know at what speed that is operating. So, you would know that velocity along the line of action of that actuator. It is unlikely that you would know both omega of the actuator and the line, okay, because that will typically not be an input. If this is the actuator, this is what you are going to give. You are going to give it a velocity along that direction. Okay. So, that is what the auxiliary point method helps you to do. Okay. So, now we have looked at graphical methods which so can give you a quick, they are fairly quick, intuitively they are quite intuitive, and so they can give you, if you are only interested in a few positions and you know the position analysis, they give you a good idea of how the mechanism is going to move. We will look at the analytical methods. Now, the idea is, okay, can we solve, you have already seen, I will quickly just go through. So, I have O2, O4, AB. Here old friend the 4 bar you have. So, we do the loop closure. Okay. So, say this is linked to, say I can okay. So, I have R2 plus R3 equal to R1 plus R4. So, I have R2 R1 e power I theta 1 plus, assuming position analysis is done, you know all the thetas, you know all the r's, you know all the thetas, you differentiate with respect to time and you get R2 omega 2 e power I theta 2 plus R3 omega 3 e power I theta 3 equals, the fixed link does not change. So, you have theta 4. Okay. Now, you should be able to recognize this. What is this? This is the velocity of A on body 2, which is the same as the velocity of A on body 3, right. This expression here is the velocity of B with respect to A, and this here is the velocity of B on body 4, which is equal to the velocity of B on body 3. So, remember the vector equation that we solved for the graphical analysis, it comes directly from these equations. You have velocity of B on body 3 equals velocity of A on body 3 plus the velocity difference B on body 3 with respect to A on body 3. So, this is where that comes from. So, again you have two scalar equations in the unknowns. What are the unknowns here? Omega 3 and omega 4. Remember, omega 2 is your input. It could be, I mean, if it is a mechanism that is driven by the coupler, omega 3 could be the input, does not matter, but you need one velocity input, and using that you have two scalar equations and two unknowns. So, you can solve for the other two angular velocities. Okay. So, this is our 4 bar. Slider crank. So, I have R2 plus R3 equal to R1 plus R4. R2 e power I theta 2 plus R3 R1 plus I R4, because we choose R1 and R4 such that R1 is along the sliding path, parallel to the sliding path, and R4 is perpendicular to the sliding path, okay, because it is easier to handle it by separating out the sliding motion from the because R4 remains constant. So, again now when we differentiate with respect to time, the nice thing about the velocity equations, if you look here even for the 4 bar, is that because the position analysis is done, the theta 2, theta 3, theta 4, they are all known. Okay. These are linear equations, 2 linear equations in unknowns omega 3, omega 4. So, velocity analysis is easy to do once only the position equations are non-linear. Velocity equations become linear. Okay, so, here now when we differentiate with respect to time, I have R2 omega 2 e power I theta 2 plus R3 omega 3 e power I theta 3 is equal to R1 dot plus 0. The offset does not change with time.
From the reunite
Where?
I omega right?
Oh, right. Here it all gets cancelled out, but here it does not. Thank you. So, here also it is there, but what happens is it will get cancelled out, but yeah, here it does not. So, thank you for pointing that out. Okay. So, now when you look at this is the velocity of what is this, the velocity of A on body 3 or 2. This is the velocity of B on body 3 relative to A on body 3, and this is the velocity of B on body 3, absolute velocity of B on body 3, because it moves along the slider path. So, this is again the same equation that we used to construct your velocity polygon. Okay, so, that follows from this. So, if you forget how we got that, this is how you get that. Okay. So, that gives you this. Again you can separate into real and imaginary parts and solve for what are your unknowns here, omega 3 and R1 dot, okay, given omega 2. Could be R1 dot is your input, that is also possible, in which case you solve for omega 2 and omega 3. Either way you get, it is a set of linear equations. Okay. Because position analysis has to be completed before you do the velocity analysis. The third one that we looked at earlier was this case, the inverted slider crank. And link 3, this is link 4. So, I have R2 equals R1 plus R4, my loop closure equation, R2 e power I theta 2 okay. Now, when I differentiate with respect to time, I have I R2 omega 2 e power I theta 2 equals R1 does not change, and when I differentiate this, R4 e power I theta 4. Okay. This is different from the previous case because R4 is no longer constant. Okay. This point R4, the length R4 is no longer constant. So, I have an R4 dot okay, e power I theta 4 plus I R4 omega 4 e power I theta 4. Now, if I look at this is the velocity of A, okay, A on body 2, which is equal to the velocity of A on body 3. What is this? This is the velocity of A on body 3 with respect to A on body 4, the coincident point at that particular instant. So, this is your slip velocity R4 dot, and it is along the link 4, okay, plus this velocity here is the velocity of A on body 4. Okay. Remember what we used coincident points to set up that vector equation earlier. It follows directly from the loop closure equation. Okay. Essentially again vector equation, two unknowns, solve for what would be your unknowns? Slip velocity and omega 4 given omega 2. Okay. Or if you know the slip velocity like we had in the case of a hydraulic actuator, then you can find the other two components of the velocity. You can find the other two omegas if you know this. Okay, because this, you know, this could be configured as like this, right.